Hello everyone. In this video lecture of part 3 on mass transfer, we'll learn about the convective mass transfer. So in this video lecture, we'll see volumetric mass transfer coefficients termed as KLA and KGA for liquid and gaseous systems, and we'll establish a relationship between them to obtain overall mass transfer coefficient. Something that we have learned in heat transfer also, like individual heat transfer coefficient, individual heat transfer coefficients, and overall heat transfer coefficient inside and outside. So very similar to that, we'll have liquid and gas system here, for which mass transfer coefficient will be measuring or evaluating, and will try to establish a relationship between them along with the overall mass transfer coefficient. We'll also see some applications of this mass transfer in biosciences. So moving ahead, first let us understand a convective mass transfer in gas liquid system. So from two film theory, we have understood that whenever there is a bulk gas and bulk liquid coming in contact with each other, and a molecule uh, transfer or diffuses through the gas to liquid or liquid to gas, you come across a thin film. That is, a gas liquid interface will be there. Across the interface on both the side, there is a gas film, there is a liquid film. Now these two films will be the major resistance to the mass transfer in this particular system. As an example, we have taken gas and liquid. You can also take liquid liquid, solid liquid, or solid gas system also. So for our understanding, at the basic level, we will consider only the gas liquid system, which is quite common in bioreactors, where we are going to learn about oxygen mass transfer into the broth later in the part 4. So as a precursor to that, we'll learn about gas liquid interface and how the resistance is offered over here. Let's learn more about it. If we draw a concentration profile, an interface, I'll draw it here. The distance from the interface on the liquids in the gaseous side here, on the liquid side here. It's a flip of this image actually. So the concentration gradient exists. You can see that concentration changes with respect to the distance from the interface, and here also in the gaseous phase that's also true. You can see that concentration in the gaseous phase is high than the liquid phase. So the mass transfer here, it is taken from gas phase to the liquid phase. When it is being transferred at the interface, it has got a concentration CAGI. A stands for molecule, the suffix A stands for the molecule A, suffix G stands for the gas phase, L stands for the liquid phase. So the molecule A has different concentration in the gas phase as well as liquid phase. And you observe here that at the interface, there is a sudden drop of concentration of molecule A from gas phase to liquid phase. It is not equal. The reason is it depends upon the equilibrium composition, that is the equilibrium constant that is going to be there, which is the in fact we develop it using the Henry's law later. And one more thing that is governing here is the solubility of this molecule A in gas phase and liquid phase. If the solubility of molecule A is very high in gas, this interface value will be very high compared to liquid. So if the mass transfer takes place from gas to liquid, the gas side concentration profile will be higher than the liquid side. If the mass transfer takes place from liquid to the gas, it is just inverse. That is, from liquid side it will be higher, for the gas side it will be lower. So depending upon the direction of mass transfer, the mass transfer starting from the starting part will have higher concentration profile than the ending part. So the mass transfer here, it is taking place from gas to liquid. If at all it was liquid to gas, exactly the opposite direction it would have been. That is, liquid side will have the more higher concentration profile, and the gas will have the lower concentration profile. You can apply this concept to any of liquid liquid, solid liquid, or solid gas system. As an example, you have extraction, drying, distillation, or even you can have the case of adsorption. right? So all these mass transfer operations, when you consider, you can use this particular concept. So let us develop certain equation for these situations or systems. In our example here, we are taking, remember, we are taking only the liquid phase and gas phase. The mass transfer is taking from gas to liquid phase. This is our case throughout. It has to be noted that the same concept can be considered or you can extend to other systems also, as I explained earlier. Since the mass transfer is taking through convective mass transfer here, there are two phases and this phenomenon is called as convective mass transfer. The mass transfer rate, NAG, mass transfer rate for molecule A in gas phase, that is here, will be given as by the convective mass transfer equation, that is Kg, mass transfer coefficient in the gas phase, into the interfacial area, this surface area of interface through which the mass transfer is taking place, multiplied by the concentration gradient, the difference in concentration, higher concentration minus lower concentration till the interface. Same way, at the liquid boundary over here in this liquid film, the rate of mass transfer can be given as the mass transfer coefficient KL for this region multiplied by the interfacial area A multiplied by the difference in concentration, that is higher the concentration minus lower concentration. So always this difference, observe it, higher minus lower. So CALI higher than CAL. So this particular concentration profile plays an important role when you write these two equations. So based on where it starts, where it ends, you should be able to write the differences in concentration. Let us consider a steady state operation here. If we consider a steady state operation, the rate at which the mass transfer is being taking place in the gas phase should be same as the mass transfer that is taking place in the liquid phase, liquid film here. So the mass transfer rate remain constant throughout both the strips or both the films. So these two equations are equal. That's what it means. NAG is equal to NAL. Now these Kg and KL are gas phase. We call it as gas phase mass transfer coefficient, liquid phase mass transfer coefficient. In reality, what happens is this finding out this interfacial area is very difficult because it is slightly dynamic. For that reason, we club KGA and KLA, we call it as volumetric mass transfer coefficient. So KGA and KLA put together, or KGA is called as volumetric gas phase mass transfer coefficient, and KLA we call it as volumetric liquid side mass transfer coefficient. So let us make two assumptions here. One, the phase boundary over here is under equilibrium condition. This is under equilibrium. So at an equilibrium, let us do the analysis. And also, before we do that analysis, let us say the dilute concentration, the concentration of this molecule is very dilute here. And because of that, a linear equilibrium exists. And that linear equilibrium, we can write it as CAGI is equal to M into CALI. So this equilibrium composition in the gas phase, equilibrium composition in the liquid phase. If you remember, we had written similar kind of equation for adsorption, extraction, equilibrium curves, or even distillation. The equilibrium curves you have, there the curve could be linear or non-linear, but in this case, we'll consider it as linear passing through origin. The slope of that is m. So this m is called as equilibrium constant or distribution constant. Usually, this is followed through the Henry's law. Rawls' law and Henry's law you may be knowing. For a dilute concentration, the relationship between the two will be linear. So that is following a Henry's law. Equivalent to that, we will be using it. So these equations, mass transfer equation, two equations here, and equilibrium relation. This I'll take it forward for doing a derivation where I am going to relate this Kg and Kl, because two phases, even though it's at two phases, the rate of mass transfer remains same here. So I'll relate that with the equilibrium condition and try to arrive at some analysis where we can club them together and call it as overall mass transfer coefficient. To begin with, the three equations which I mentioned, I have written it first. That is the mass transfer rate for molecule A in gas phase, mass transfer rate for the molecule A in liquid phase, and equilibrium relation. Three equations I have written. So what I'll do is this CAGI and CALI, these two terms, when it is appearing in equation 1 and 2 over here, CAGI and CALI, these two terms I'll replace using this equation. So what do I get? Nag by kga is equal to Cag. The Cagi I'm replacing now. MCALI. I'll call it as equation 4. Same way, the CALI I'll replace it using the equation number 3. NaL by KLa is equal to the CALI I'll replace, that is Cag by M minus CAL. So I have two equations. I have modified these three equations to get two equations. So let us further do some algebraic conversion of equation on 1 and 2 by dividing m. The reason here is the CALI and CAGI interface concentration. It is practically difficult to estimate. Estimating these two concentrations is practically difficult. For that reason, we should be able to get rid of these two terms. That's what we are trying to do here. So what I'll do is algebraic and relation. I'll try to get it. One equation, original equation, one of the equation I'll divide it by m, another equation I'll multiply by m. So what I have done here is equation 1, which is for the gas phase, I have divided by m. Equation number 2, which is for the liquid phase, I have multiplied by m throughout. So what do I get is Nag by m into kga, both the denominators m is there. Then multiply the second equation, that is NaL by KLa, NaL by KLa multiplied by m. Both the terms inside the bracket, you have the multiplication of m. So equation number 6 and 7, I get it. Now let me club equation number 6, 7 and 4, 5 in a particular way. And let me not forget that these two rates, Nag and NaL, both are equal. Instead of writing Nag and NaL separately, I'll consider writing Na for NaL and Ng. So what I am doing is equation number 5, that is for the gas, this is for the liquid phase, and equation number 6, which is for the gas phase. So I have done two algebraic modification here. One using the equilibrium relation, I got two set of equation. Another equation, two set of equation I got by dividing it and multiplying by m. Now I'll club two set of equation. Equation 4, 5, one set. Equation 6, 7, another set. When I'm clubbing them, I'm adding them. What I'll be doing is one of the gas phase equation, I'll relate it with the uh, liquid phase. For example, here it is liquid phase. Equation number 5 is liquid phase. Equation number 6 is gas phase. How I am trying to identify it? I am identifying this term. I do not want CAGI and CALI here. I have to get rid of these two terms. How can I get it? If I observe equation number 6 and 7, same CAG by M here, this term is present over here. And it's minus, this is plus. So if I add them, these two terms gets cancelled out. So I'll get it. Get a real equation for that. Now if you observe equation number 4, M into CALI, it is negative. And equation number 7, it is plus MCALI. If I add these two equations, I can get rid of the CALI. That is my target. So equivalently, when I simplify that equation, what do I get? Na, instead of Nag and NaL, I'll be writing Na. I'll be combining the two equations. Left hand side, let me combine it. So that is equation number 5 here. It is 1 by KLa plus 1 by MKGA, 1 by MKGA. That will be equal to CAG by M. This CAG by M gets cancelled here. This term gets cancelled. This term also gets cancelled. Minus CAL. That remains. Equivalently, equation number 9 also, you get it. Now, these two equations, let me carry it forward so that I can relate some more things here. So, if you observe the same equation, the equation that we got, equation number 8 and 9, are rewritten here. The same equations are rewritten. This equation, I'll write it as like this, in this form. How did I write it? The mass rate, right? The mass rate of molecule A, whether it's liquid or gas phase, doesn't matter now because both are same. The mass rate, right? The rate of mass transfer of A will be equal to this capital K. You observe it, this is a capital K. So overall mass transfer coefficient or overall volumetric mass transfer coefficient, let me call it as volumetric, overall volumetric mass transfer coefficient multiplied by Ca star Al minus Cal. I have written this way. What does it mean now? This KLA, how do I get it? This KLA, I can write it as 1 by KLA is equal to 1 by m kGa plus 1 by KLa. How did I get this equation? Look at the equation number 9. This equation number 9, I am equation number 8. If you observe equation number 8, I have rewritten this equation. So what I have done, 1 by mkga plus 1 by KLa. 1 by m, it is here, 1 by mkga plus 1 by KLa. It is equal to 1 by KLa. I am rewriting these two terms as 1 by KLa. So I'll replace it, this two term, with 1 by KLa. So this equation, when I'm writing Na, that KLa can be taken on the other side. But in the bracket here, you have CAG by M minus CAL. CAG by M, I'll rewrite it as equilibrium composition. CAG by M is equivalent to equilibrium composition. You can see here in the right bottom, liquid phase equilibrium composition. So equilibrium composition means there's a maximum concentration A can reach in liquid. Maximum concentration of A that can be reached in liquid, nothing but solubility of the component under that experimental conditions. So that will be equal to CAG by M. M is the same M which we have related earlier called as Henry's constant. It is the same M. Equivalently, I can write the equation number 9 as Na is equal to kGa into CAG minus C star Ag, where this 1 by kGa plus M by KLa, I will write it as 1 by kGa. That is, kGa is nothing but overall gas phase mass transfer coefficient. So that I'll be replacing. Very exactly similar to what 8 it is converted here, same way for 9. So here C star, what you get, C star Ag is the equilibrium composition. That is the solubility of molecule A in the gas phase. These two equations, what do they represent? These two equations represent mass flow rate or molar flow rate or molar rate or mass rate, you can say, any depending upon the concentration terminology that we use here. So rate of diffusion or rate of convection or mass transfer, convective or diffusive mass transfer that is taking place in the entire system here, if you analyze at the liquid state, liquid phase, if you analyze only at the liquid phase, you need to know liquid side overall mass transfer coefficient multiplied by the equilibrium composition minus its actual concentration. If you observe on the gas phase, if you want to do the analysis on the gas phase, you need to know the mass transfer coefficient Kga, and you need to take the difference between the actual concentration Cag minus its equilibrium composition. So based on these two conditions, either on this analysis, liquid side analysis or gas side analysis, you will be able to perform an analysis. This is how the right top, what you see here, overall mass transfer coefficient can be written either in the gas phase or in the liquid phase. In reality, what happens is both will not be equal. One will be large, one will be small. That is, either it is KGA or KLA, one of them will be small and one other will be large. Our intention of overall analysis is to find where exactly is the high resistance available, mean which particular phase, whether it is liquid side or gas side, where the high resistance is present for the mass transfer. So that we try to address. So the one which is very low, kga or kla, one which is very low is of prime importance for us. The one which is very large means it is having no resistance to the flow. It has no resistance. When the kga is high, no resistance to the flow, it will transfer. So we don't have the problem. But if KLA is very low, it means it is offering high resistance. If there is a high resistance, overall process is slowed down. We should not want, we should avoid that. We don't want slowness of the overall process. So we should address KLA part. So the overall analysis will help us in identifying where exactly is the resistance lying. Let's move on to the some applications. Let's see for the mass transfer, specifically the convective and the diffusive mass transfer in biosciences. In the case of food processing, if you see the food processing, diffusion is highly used. Diffusive or convective mass transfer, like for drying, evaporation, extraction, emulsification, or food respiration. In these cases, it's highly useful. Fermentation processes, like in this diffusion of nutrients, sugar, oxygen, enzyme within the fermentation broth, diffusion concept is applicable. In pharmaceutical and bioprocess industrial applications, colloids play a major role. In protein macromolecules, they interact with the solute. That's called as transmembrane interaction across the membrane, active or passive transport, and protein ligand interaction. maybe like hemoglobin attached to the oxygen, this kind of analysis, or renal dialysis, or electrophoresis, chromatography, or gel permeation. These are all chromatography and electrophoresis technique. In all these cases, diffusion play a major role. In fact, some of these are two-phase systems where gas chromatography, liquid chromatography, HPLC. So all these places, adsorption, these are all uh, preliminarily based on either diffusive or convective mass transfer. One important aspect, that is oxygen mass transfer in aerobic fermentation. This is one of the very important topic that we are going to deal or learn in the next part of this video lecture series. So oxygen transfer, we will be analyzing where exactly is the resistance lying and how do we tackle it or how do we estimate all those things. We'll learn it in the next unit. So, what did we learn here? We have learned different volumetric mass transfer coefficient KLA and KGA. We have understood the relationship between them, and also we have related it to the overall mass transfer coefficient. We have observed that some of the biosciences systems have applications from mass transfer concept, that is diffusion or convective mass transfer, have large application in biosciences. One among that, that is oxygen mass transfer in fermenters, will be concentrating upon in the next part of the video. That's it for this video lecture. Thank you.